I think. Yeah. Okay. Welcome to week number 3, believe it or not. This is like time flies. With that, I'd like to start the discussion on your meter, which is also approaching. As you know, okay, that's better. As you know, the spring break is when? I guess you are all workaholics, so you do not know what the spring break is. But I'll tell you, because I looked it up just now, is March 16th, right? March 16th. Your midterm is going to happen on Friday before your spring break. Yeah, whatever the date is. I think it's March 13th. Huh? March 13th. I will, of course, post this in your Discord as well, so you have it there. Most likely, I won't be there. I won't be here during your midterm, but the TAs obviously will. Good luck with your midterm. All right. So with that said, let's get started. As a reminder, you have an assignment for this Sunday, right? Make sure that you are not involved in any discussion like, oh, I got a 0 after the assignment is grades are posted because I forgot. That's a class. I forgot that I have to add the TA as a collaborator. I forgot I had to submit the GitHub URL in Brightspace. I forgot this and that. Okay. So make sure you submit your assignment. You read very carefully what you need to do to submit your assignment. Okay. In the instructions posted, how to submit your assignment. Okay. It cannot be clearer than that. Okay. So today we are going to recap what we were doing last week, and we will move on into finishing off the statistical learning theory part of the course with the introduction of classification. And let's see how that goes. And then from week after the next week, we will start neural networks. Okay. All right. So expect also your new assignment to arrive sometime early next week in your inboxes. Again, we will give you 2 weeks to finish it. This next assignment won't be as easy as this one. Okay, I told you that already. All right, so let's get going. So can I ask you, last time, okay, we went through some kind of probabilities, but I want to start with this thing over here. Why we had this kind of discussion, what we're trying to do, what is this? Why we started talking about maximum likelihood all of a sudden? Yes. Because we would like to look smart by using some kind of strange sort of technical terms. Probably not. Because as I told you, we are in the business of relaying to the customer uncertainty about our predictions. That's the only reason. Okay, so we were introducing statistical models to augment the deterministic models that we were dealing with up to this moment in time. Specifically, we were going back, or we will go back to linear regression, and together with the house price, right, we will tell the customer, I have a confidence of plus or minus $50,000, for example. Okay. Or when we look at images later on, we will tell the customer, I believe you have cancer with probability at 0.95%, which is interesting. Okay, so we started this discussion on kind of maximum likelihood because we decided that out of this augmentation we have done in the Vapnik plot diagram, the one that we wrote, these probability distributions, the orange ones, and 2 probability distributions are of interest in this class. Which ones are those? 2 main probability distributions are of interest for us. We should always know their name and what they mean. Yes. Sorry? The Gaussian distribution. There's no Gaussian distribution here. However, instead of a Gaussian distribution, what is the name of the distribution here? P what? P data. So I hope you are watching the videos now. Interesting. Someone came to me a few moments ago and says, you know, we have no permission to watch your videos, right? But also very interesting, no one raised that fact in Discord as well, which of course this tells me you never watched that video because obviously no one could watch the video. So you should be reviewing what we are discussing here, at least at the headline level, and augment your own kind of notes and ask the why questions. The midterm is in 4 weeks? No, it is in 5 weeks. But 5 weeks is the midterm, which means that you need to be preparing for it, right? So you have 4 weeks to prepare. All right, so with that in mind, P data of what? P data of X is of interest to us, or P data of Y given X is of interest to us? Why? Why is that of interest to us, the P Y given X? Which is the question you have to write in your notes down, right? The reason why the P data of Y given X is of interest to us, which is called the conditional probability distribution of the data, is that we are in the business of making predictions. Are we making predictions about the X or about the Y? About the Y. So if I give you a conditional probability distribution as we were reviewing it last week, anything before the given symbol is a random variable, and anything after it's not. And therefore, obviously, we are going to be predicting the Y's. And therefore, we call these predictions Y hat for this reason. With what are we going to do the predictions? Using what? Well, we are using, obviously, someone will give us the X, right? And therefore, we need to build a probabilistic model that we call the P model, that when someone gives you the X for a given set of W's, and an X you've never seen before, you are able to do a prediction by sampling out of this probability distribution. Sampling is what is going to happen. That's how we will make the Y hats. I hope everyone understands what sampling is. Okay. We did it last week. I'm not going to review it. It's now done and gone. All right. So we went into this kind of discussion in order for us to understand. First, we understood already we need to come up with a hypothesis, which is now a probabilistic model. That's one thing. The other, we need to also have an objective function, a loss function. We need to derive an objective force slash loss function, which now captures the distance between ground truths and Y hats. This cannot be Y hat minus Y, although the mean square error, as we saw it initially and presented it in that's a kind of a hand-wavy way, will be derived out of this more elaborate statistical loss function we will derive today. The bottom line is that let's try to simplify the problem by forgetting a little bit about a prediction problem and looking at a much simpler problem, which is a density estimation problem. In other words, we don't have any Y's here. We only have X's. Someone gives you some X's on the real line and asks you the following questions, which is written on the Can I move this thing? Yes. As it turns out, I can. Okay. Give me what it says here, give me a P model that fits the data. That's the question. So what Vabning suggested to do, to come up with a block that's called hypothesis set, right? And the hypothesis now is not a function as it used to be, right? But it is what? A probability distribution. This probability distribution now is suitably chosen. And when I say suitably, is we need to look at what we are trying to model, which is called X here, and see, is this discrete or continuous? Is X discrete or continuous? Okay, if we are not able to answer this question, I'm foreseeing lots and lots of issues. Lots and lots of issues with your grade, not me, but for your grade. So X is what? Is this a real number? And therefore X is a continuous random variable. Okay. What we are seeing here are not are samples out of a continuous probability distribution. Therefore, our P model is our hypothesis, in other words, has to be a continuous probability distribution. Give me examples of continuous probability distributions. Normal, chi-square, beta, whatever. Take the Wikipedia statistical distributions kind of dictionary and read all the continuous probability distributions out. Any single continuous probability distribution can be a suitable hypothesis for this problem. Out of the many, someone, I in this case, selected the Gaussian because I am obviously a good person, polite person, so I don't want to throw to you some kind of a weird probability distribution that is no one understands what's going on there. So we need to understand that. We need to understand that it's our responsibility to select the P model. In fact, we will be constructing the P model itself very soon out of elementary units that we'll call neurons. But right now, the P model takes the form of a Gaussian. And I'm suggesting that this hypothesis, which is written here with an equation, has an equation just like the polynomial thing that we had earlier, right? If you remember in the regression kind of setting. And obviously, this equation had a set of parameters. And now here we also see a set of parameters which are still called W. And how many parameters we have here? We have 2 parameters. So obviously we need to determine the mean and the variance of this hypothesis such that the question is answered. The moment I have an equation as a hypothesis and a set of parameters in that equation, the question changed to this. What are those parameters should be such that we have a good, nice histogram plotted right on top of the data. That's how intuitively we capture what we are after. That's why we call the problem a density estimation problem. Am I recording? Yes. All right. Good. So the moment we have a parameter estimation problem, how we solved the parameter estimation problem earlier? How? By pressing the play button on a notebook? No. By posing an optimization problem statement and forming an algorithm that we called, what was the name of the algorithm? Gradient descent. Yes, stochastic gradient descent. Stochastic gradient descent. That was the name of the algorithm. To find the W star. So are we going to do the same thing here? Yes, we are. But the question became, before we had some mean square error, we came out of nowhere, right? To calculate the gradient of the mean square error and call this SGD with that gradient. To calculate the W star, now we need an objective function. Because every single optimization problem is posed as objective, subject to constraints. Maximize or minimize an objective, subject to constraints. Sometimes the objective is also called cost. You may have heard about the optimization problems, primitive optimization problems in your previous life. Even if you haven't, that's fine too. We are after now that objective function. Are we okay now to proceed with that? Any questions up to this is now the problem setting. We are going to derive an objective function that makes intuitive sense, and then we are going to solve it. All right, I think this is where we stopped. So I'm going to draw a line over here. Today is what? 276. Okay. Now, this objective function is going to be called, it has a name. I'm going to give you the name. I'm going to write down the objective function. And apart from the name, we need to understand the intuition behind it. It's called likelihood function. The objective function is going to be called likelihood function. And the likelihood function of what? Function of the parameters. That is the answer. Function of the parameters. So this function, likelihood function, is P model of X. X, remember, is this set of data that I gave you. I wrote it over here. Okay, given W is describes how likely all the samples given as data how likely the samples given as data are generated from the hypothesis. In the previous weeks, or last lecture, we did an experiment. Someone gave you a document called the Linux FAQ guide, and in our discussion about entropy, we did the following kind of experiment. Someone, or we did even a coin tossing experiment, if I remember right. Someone was tossing a coin n times and was calculating probability of heads and probability of tails, right? Probability in this kind of setting is a quantity which does not depend on anything other than the outcomes of that experiment. And the way it is estimated is I'm counting how many heads came out of this experiment, divided by the number of samples that tosses that I did, and that's it. Likelihood, on the other hand, is almost like an inverse kind of probability in a sense that it does not really answer the question. It does not answer the question what is the probability of x1? What is the probability of x1? If I ask you the question, however, what would you say? What is the probability of x1? x1 is a real number. The probability of x1 is exactly 0. Because x1 happened as an event, and I have an infinite possible events that I can potentially have, right? So this is basically the probability of any real number is 0. The probability of meeting a very specific number is 0 in this kind of space of infinite possibilities, right? So likelihood is different than kind of probability in a sense that it answers the following question: how likely is this event to have been generated out of this hypothesis? So there's no, contrary to probability, that doesn't depend on anything on the outcomes that we have. Likelihood depends entirely on the hypothesis. If you don't have a hypothesis, you don't have any likelihood. That's why we can actually safely write that the likelihood function is grounded on the hypothesis. In other words, on the equation, the shape of the hypothesis, and the parameters, of course, where the hypothesis is now located, so to speak, at this moment in time at least. And obviously, to evaluate it, the likelihood, let's say, of x1, you can go and plug in instead of x1 over here, and plug in the specific hypothesis mu0 and sigma 0 squared that we're evaluating the likelihood of x1. And you have what? Do you have a number out of this equation? Yes or no? You don't have a number. Yes, you do have a number. It's a number. It's a very small number. It's a very tiny number. It's very tiny because look how far away x1 is from the hypothesis. It's like 10 to the minus 100, something like that. Right? Now, however, over here, we have a likelihood that involves now many. So not only I gave you x1 only, I gave you x2, x3, x4, all the way to xm, right? So we have to make a simplifying assumptions to be able to compute the likelihood function for all the set, for the set that someone gave us, right? So what is how we are going to go about doing that is as follows. We're making the assumption, which stands for, probably you've seen it in many textbooks, IID assumption. It stands for independent, identically distributed. In other words, the samples x's that I gave you have no correlation with each other. When I'm sampling, I'm not considering what I had before in order to sample the next one. They're independent. This independence will be connected to the product rule soon and allows us to effectively simplify the likelihood function greatly and evaluate it in a simple way. And identically distributed comes from the fact that, you know, there is an underlying. Probability distribution, P data hat we called it, right? Or P data of X, avoid confusion, that generated the points. Like a Gaussian random number generator was there, right? This Gaussian random generator has some kind of mean and variance. We do not know if it was Gaussian, beta, or whatever probability distribution generated data, right? We do not know any of the parameters. We do not know anything about the blue hypothesis, the blue probability distribution. But what we are assuming over here, this is disappeared. What we are assuming over here is that probability distribution, the P data, could be very, very complicated, but it's only one. Identically distributed. In other words, all the samples came from the same probability distribution, not a different one. That is the English interpretation of IID assumption. Very common to make, and to some degree, mild assumptions. Some other people have an issue with independence, right? And therefore, they consider to be a strong assumption, but we will bypass this fact for this class. Okay. So, are we following what's happening now? We introduced likelihood as a tool that it will give us an evaluation function, just like the loss function was playing before, the roll-off, to evaluate every single hypothesis. It will evaluate the white hypothesis, and it will evaluate every single hypothesis we throw at it. How? It will always come back to us with a number that is going to be greater than or equal to 0. Okay, that's how it is going to be from that perspective. So let me write down a couple of things. All right. So first of all, in a kind of a box over here, I can write that likelihood is grounded to a hypothesis, likelihood function is grounded to a hypothesis. That's one thing that I mentioned. And the other thing, of course, I mentioned is I will take this kind of assumption to go from here, from this expression to something which is easier to calculate. Okay. And I want to remind you about the product and the sum rule. The product and the sum rule. In the case we had this discussion about that last time, right? We had this discussion last time, so I'm not going to have this discussion. Did we have this discussion? No, we didn't have. I don't see any discussion about independence last time. So let me have this discussion kind of briefly. Okay, so what is really the product and the sum rule? Okay, so not what it is, but how we're going to use the product rule. What is the product rule? P of x comma y is equal P of y given x times P of x, correct? That is the product rule. Okay. Those who do not know it, they will have a difficult time, understanding how it is used and why it is used and how we will get out of difficult situations such as this one to make our lives easier, computable, in other words, right? So, so let's assume now that I'm dealing with an independence example, right? So let me give you some independence example. Let's assume that y is the Tesla stock price and x is the weather outside of you can do it, New York Stock Exchange. Okay, that's it. So what can you say about this P of y given x? What is this equal to? P of y, thank you. So in this kind of situation, when P of y given x is equal to P of y, is when we have two complete. I mean, in other words, knowing the weather outside of stock exchange does not really offer us any information, does not really change anything about the P of y. Okay, are you following? So if I write this last equation, how is this P of x comma y can be written? In this case, P of x comma y is equal to P of y times P of x. Do you agree? If the last equation is considered, that's exactly what I'm writing. What the result. So the joint probability distribution can be factorized into the individual marginals to make the life easy for us. So we are going to use this kind of probability that IID provided to us to write one. I'm going to title this one, and I'm going to write one is equal to P model of x1 given w times P model of x2 given w times dot dot P model of x m given w. Do you agree with what I wrote, given all the previous discussion we had about independence? Yes, you agree or disagree? Anyone disagrees? I guess not. All right. Anyone has any question whatsoever? You seem to have been in some form of a shock, of some kind of shocking situation has just happened. Nothing happened here, really. Everything is kind of straightforward out of basic sum and product rule that I told you to review so many times. I'm going to stop suggesting to watch that video. Okay. So we have now, and a few moments ago, you told me that I can evaluate this guy. I can go to the P model take the equation, plug in instead of x, x1, plug in a specific w that the specific hypothesis is telling me that it is located right now, the mu 0 sigma 0 squared, and come up with a number. And for the white hypothesis, you told me this number will be very, very small. Now, just to test things out, is the likelihood of x2 is going to be larger or smaller than the likelihood of x1? Larger or smaller? That's how we test, we understand. The likelihood of x2 will be larger than the likelihood of x1 because it is closer to the left tail of this guy. And the likelihood of x3 larger, xn. And if there is a data point over here, it's going to be pretty large. Okay. So then we're going to have, I don't know, 10 to the minus 90 times 10 to the minus, 78, but so it doesn't really matter. Bottom line is that any computer facing a product of this type of numbers will underflow. So in all probabilistic calculations, we are using an interesting transformation called the log transformation. That you know it from elementary school. Log of A times B is equal to what? Log A plus log B. Okay. So this transformation will be used to avoid this underflow possibility. Luckily for us, log is a monotonic function. That's why it doesn't go up and down. It's monotonic. So which means that if I do this transformation and I have an objective function that I do the transformation in the log domain instead of the absolute domain, the location of the optimum will not change, will be exactly the same W star. So I'm in a very good shape by this transformation. I avoid underflow. And if I choose the log to be, if I write those 10, I write e to the power of minus 100, whatever. And I choose the log to be the natural log. This product becomes now a sum of minus 100 plus minus 90 plus minus 78 and so on and so on. So I don't have an underflowing. For this reason, likelihood functions is going to be called log likelihood for this reason. Probably you have come across some books that talk about log likelihood. All right, so we are going now to sort of write this log likelihood then as we will designate it always as LL of W. Okay, and we are going to write it as summation from I is equal to 1 to M ln P model or log, it doesn't really matter, of Xi given W. Do you agree with this transformation, how the product became a summation? Okay. And now we have, we are fortunate because of the initial thing that I told you about choosing this kind of Gaussian. We're very fortunate because inside this P model, the Gaussian P model, I have an e to the power of something. And with the ln in front, there are certain cancellations that are happening, right? And the functional form of the log likelihood function is going to look like this. For the specific, this is a general formula, right? This is a general formula. But for when it's a Gaussian, I'm going to write it as minus 1 over 2 sigma squared summation from I is equal to 1 to M. The specific equation does not really matter. The only thing that matters here is to be able to go into some kind of Python code to understand what it looks something quite complicated is in fact a single line of code. If we make this kind of mapping, we can see how can evaluate trivially a log. Did someone call me? How this happened? Where is it? Here. Okay, I was suggesting that we will go now to a Python code to see how this thing can be evaluated trivially. And in fact, let's do it right now. Let's do it right now. Where is it? Foundations, margin and MLE. Oh, interesting. Someone is giving you some data on a real line. Okay, these are the blue dots. And he's asking you, I have two hypotheses, in other words, two probabilistic models that I would like to consider, the blue and the red. Which one is the most appropriate? Is this a reasonable assumption? Yes, it is, because at the end of the day, we have to come up with a P model. Here I'm giving you only two choices, like a multiple choice thing. I'm not telling you what is the best optimal thing to do. This will come. But between the two choices, which one is the best? Okay. A better model for you. And in fact, I am constraining this hypothesis, these two hypotheses I'm actually giving you, to be Gaussian. One of them has a parameter of, I think both of them have the same variance from what I can see. One of them has a mean of 5, and the other, the blue, has a mean of 7. Everyone has any questions on the problem we're trying to solve here? Okay. So, this is the evaluation function. We are setting the log likelihoods to 0. And we go. Just like the equation you just wrote down in your notes, summation from I is equal to 1 to m, log of the P model, correct? That's what you wrote. Summation from I is equal to 1 to m plus equal log of the P model. The P model I told you is Gaussian. Therefore, instead of writing 1 over 2 pi square root blah blah and so on, I'm writing norm.pdf, and norm.pdf comes out of SciPy package. Yes.
The question did not give us like the standard deviation for the two lines. So how can we find out the log length?
I'm telling you that the standard deviation is given. Is here. This guy, STD1, STD2. I'm plugging in numbers specific for the specific in the function call. Do you see the function call? I'm plugging in the standard deviations. They are given. I just didn't mention it verbally, but they are given. Both means and both parameters of the both hypotheses are given. I'm just evaluating them. Is something missing from the evaluation? The answer is no. Everything is there in a single line of code. So if you run it, this is going to be the result. The question is, which one are you going to choose? The lower or the higher?
Higher log likelihood.
The higher log likelihood for this very reason. Between hypothesis, between a hypothesis that is far away from the data, like the white, and a hypothesis which is closer to the data, right? The log likelihood of the green will always be higher than the log likelihood of the white, right? While these likelihoods for this xm minus 1 and xm were very, very small numbers with respect to this hypothesis, they are very large numbers with respect to this hypothesis. This is the intuition of the behavior of the log likelihood function. is going to be a concave function for the Gaussian, because you can see from when I plugged in the P model, the specific functional form of the P model, I see some really nice squaring terms, some quadratic nice terms showing up. So I'm expecting to see something like that, right? Someone has, however, to answer the question, okay, I know how to do now things when I have these two to compare. I know which one to choose. I will choose the green. But what happens when someone asks me the question, what is the best one, right? So obviously now that I have an objective function, all I have to do is to bring a stochastic gradient descent into the picture, who is unfortunately a minimizer. It's not a maximizer, it's a minimizer. And with a trivial trick, which I'm going to do right now, I am going to introduce the negative log likelihood, which is a minus sign in front of the log likelihood. And then whatever was a concave curve earlier now becomes what we call these curves, convex, just like the chi-squared function that I was minimizing last week, right? It became convex. Does the W star changes from this transformation? No, it doesn't. Wherever was the maximum in the concave curve, immediately it became a mirror function, but is now convex, and exactly the same W star is being produced at the output. So let's plot it now and see how it looks like. Yes, go ahead.
So you had in the other example, the variance is the same. What if you care about having sort of small variance? You want to compare it to?
So in the previous numerical example, in fact, the variances were different. You know, standard deviation of 1, a standard deviation of 2 was 3. Oh, sorry, they are the same. So, okay. So what happens when the variances are also different, right? Instead of plugging in SDD1 plug the numbers that someone gives you in terms of the comparison. In terms of optimization, however, right, the sigma squared is part of the W vector, right? So we'll see now a situation that answers that partially this question. This is the negative log likelihood for a case where someone is asking the question, what is the best, for the specific data points I gave you, what is the best possible hypothesis? Now, how many parameters you have? 2. You have a mean and a variance to estimate, right? So obviously then the search space is going to be the floor of this kind of room. And somewhere in this kind of room, you will see a very nice 3-dimensional convex-like plot. Negative log likelihood in the vertical axis, and sigma squared and mu to be the 2 axes over here. You're going to see something like 3-dimensional. So I'm not very good in plotting 3-dimensional plots, so I did the following. I suggested that maybe I will just plot against only the mean, keeping the variance as something that I can iterate on discrete values for, and claiming that really the mean is really a huge driving force behind the likelihood value as compared to the variance. One is obviously important here, but I'm just going to not plot it both at the same time. This is basically what I have done. And I told you that the negative log likelihood is going to be convex. And I have plotted the exact functions across the mean as a parameter only here. And obviously there is an optimal mu star that the SGD will find. The SGD will have a very easy life finding that mu star. And it will be 6 point something. Okay? Now, the variance, I'm doing multiple plots instead of doing a 3-dimensional plot. I'm doing multiple 2-dimensional plots for the variance parameter, and therefore the variance of around 2.5 is going to be the best. Are you following? That is going to be the sigma star squared, or the sigma star. Okay, so now I have the mu star and the sigma star, I'm done. So let's write down a couple of things. By minimizing the negative log likelihood, we get the optimal set W star is equal to mu star sigma star squared sigma squared negative log likelihood. And I told you it will be a three-dimensional kind of plot in this space of the parameter space, in other words. And the optimal here, W star, will correspond to, I don't know how to, a mu star over here, and actually the mu star must be like this. Mu star and sigma star squared. Okay, I hope you are following the logic here. Okay. I started with data on the real line, and I said this is now my P model. It's going to be the specific Gaussian, okay, with the W star as parameter. So, okay, and now that we have looked at this, how this will be solved. Effectively, stochastic gradient descent will take as input the gradient of the negative log likelihood. It will take as input the negative of the gradient of the negative log likelihood. With respect to W, and will move in small increments the initial hypothesis, and now it makes sense to call the white the initial hypothesis when I'm discussing about the stochastic gradient descent. We'll move with small increments towards the correct direction, which surprisingly here is the left. All right, that's basic. This is where it will stop because it found this global minimum, because the loss function, the negative log likelihood function is very well behaving, found a global minimum, and it stopped there, just like I did it with my plot. If you understand this marginal likelihood problem, you will understand the conditional likelihood problem, which is a direct extension out of this. And then you will understand exactly what the stochastic gradient descent as a predictor now, because we'll reintroduce the y variables, is producing. It will produce something to do with that kind of conditional P model, some statistic out of the conditional P model. Having said that, we will derive now the cross entropy before we go into the conditional model. We will derive now the cross entropy as the main objective function, even for the marginal problem. And then the cross entropy for the conditional problem will be a direct extension of the marginal cross entropy. And the marginal cross entropy, out of the marginal cross entropy, guess what one will be coming out? Guess what thing will come out of it? The mean square error when we do the prediction in the conditional. Okay, so here is the treatment of that. I'm going to show you only the website to avoid any heart attacks by writing complicated equations. Okay, so first equation. Who can translate the equation for me in English? First equation. No one can translate it in English. Argmax. Have you ever seen argmax before? Argmax, yes, it is suggesting argmax over W. Give me the W, right? That maximizes this guy, the P model. I gave you some data on the real line that I call this capital X, strange capital X. Then I suggested the IID assumption, and immediately the whole set became, this P model capital X became a product of the likelihoods of the individual points. Then I applied the log transformation, and immediately the product became a sum. And if I divide by 1 over m, nothing changes with respect to this optimization. If I optimize an objective for the cost of for this cost, then I'm optimizing the objective for the 1 over m of this kind of cost. The W is unchanged. And this basically is a sample mean, if you remember, right? This is sample mean, which is basically the way we are calculating here for the specific set, an expectation. So this is a very general formula for the marginal likelihood. Very, very general formula. So it translates as follows. Find the W that maximizes expectation. We never optimize something instantaneous. We always optimize something which is average. Average risk, we call it in machine learning courses, right? Average, whatever. So expectations, what expectation across all data, all x's that someone will give you, of the log of the P model. For this reason, this thing is going to be known as log loss. And another well-known term that people introduced, and it is a commonplace to call it like log loss, apply the log loss, blah, blah, and so on. Yes, go ahead.
Can you explain how you go from the first line to the second line?
First line to the second line with the IID assumption. Because I factorized the P model of capital X as a product. Remember the Tesla and the stock exchange discussion? I factorized it with this independence. Right? So I took a P of x1, x2 and I wrote it as P of x1 times P of x2 because x1 and x2 are independent. That's how I went to
define, like, for the first line, what do you mean by, like, find the W that maximizes this random variable?
It's exactly what the exercise we just did. We found a W, which is the mean and the variance in this specific example, that maximizes the likelihood. The log of the P model of the summation, in other words, the summation of the logs of the P model, the summation of the individual likelihoods of all the data points that someone gives us. This is exactly, it's like another way of writing what we have just done in a kind of a single line. You see this argmax all the time in front of you in papers and stuff like that, that deal with loss functions, objective functions, and so on, etc., etc., etc. Posing an optimization problem, you will always see an argmin or an argmax in front of you. So now this is a tricky, slightly kind of tricky part. Similar to what we have done earlier, where, yes, go ahead.
Why do we prefer to minimize the negative log likelihood?
Because we have a minimizer. We have stochastic gradient descent. We just want to use it from the library. Heavily optimized, we just use it. So if you look at the diagram, what was the end result out of this? I started from the white and I minimized the distance between two probability distributions. The P model and the P data hat. All of these are my hypotheses as the SGD was operating. as the HGD is operating, the distance between the two probability distributions is, I called it distance, but in fact, there is a quantity called KL divergence. It's not, distance cannot be called formally because it's not symmetric quantity. That captures exactly that. If someone asks you what is the difference between two probability distributions, KL divergence. How to calculate it? Go to PyTorch and type in the Python code there. Okay, it's very trivial calculation. I will show it to you. I was showing you this equation over here. This is basically the formal equation about KL divergence. Definitely, I'm going to see two arguments in the equation: P data hat and P model. Both of them are there. Tell me how much will be KL divergence when the P data hat, when the P model goes and falls right on top of the P data hat. 0. So KL divergence is going to be always a quantity greater or equal to 0. Now, Shannon, he derived another formula that defines a quantity in information theory called cross entropy. Cross entropy involves two probability distributions too, and it's equal to the KL divergence plus the entropy of the P data hat, the empirical distribution. Do you see any parameter here, W, in this? Here? No. Because there's no W inside the P data hat. There's nothing. We don't even have. So we can actually ignore this thing, and we can actually equate, specifically in our case, right, the cross entropy with the KL divergence. For this reason, either I say minimize the KL divergence between P data hat and cross entropy, and I say minimize the KL divergence between P data hat and P model, or I say minimize the cross entropy between P data hat and P model is one and the same thing. So from now on, we will be using cross entropy as the objective function for solving maximum likelihood problems. And this is basically what it is written in textbooks. Yeah, use cross entropy for classification, they say. Use mean square error for regression, they say, right? Problems. But as we will see, cross entropy and the mean square error includes the mean square error for continuous random variables. Yes, go ahead.
For the likelihood which takes in the W, shouldn't it be negative of cross entropy? On the last slide, like the formula.
Cross entropy. KL divergence had, yes, negative, yeah. Well, cross entropy is minus. The minus is in there. It is the minus came from here. Because this guy is not involved in optimization. The minus came from here. Minus expectation of the log of the model. This is what I called earlier as the log loss, they call it in prediction problems. Right now we have no labels, but we are going to introduce them momentarily. Okay. So what happens now when we have conditional P models? Nothing changes. Absolutely nothing. Instead of the P model being of X given W, the P model now is what? Y given X comma W. The same cross entropy loss can be borrowed from the marginal discussion that we just had and read it down like this. That's your loss function. Now I will call it loss function because it captures the loss of my prediction, because now I'm predicting Y hats. And I'll show you how what it should look like in the regression setting. What this brought us in the regression setting. If we are to, together with our house price prediction, let's say, go back and remember what we did in regression for the house price prediction. we started drawing hypotheses as curves. This is what we did. We came up after some discussion about regularization to some kind of a sinusoidal hypothesis that fit the data well. That was exactly what we did earlier. And we used stochastic gradient descent to plot that line. Now, we have to connect what the stochastic gradient descent is doing with what is the same situation with cross entropy as a loss will do. Okay, so let's take it one step at a time. But one thing is certain. We are going to treat now the regression problem probabilistically. I am going to suggest that in the x versus y plane, right, that I have my dots that someone gave me, I have to produce the red line. Okay, that's basically the whole problem, how to produce the red line. But at the same time, I don't just have to produce the red line because I didn't have to go into this framework to just produce the red line. I have also to produce some standard deviation around my prediction to relay some form of uncertainty, how uncertain I feel about this prediction. And so for me to do so, first, I have to write down some assumption about the linear regression problem in terms of what hypothesis it will, I will assume. So now linear regression with uncertainty. I would suggest that the data that I see, the y that someone gave me, right, came out of some underlying function, target function, that no one gave me any information about, just like consistent with what we have been telling you up to this moment in time, plus some noise, which I can impose an assumption to be Gaussian. Remember last week about the thermostat and the discussion we had about, oh, the thermostats are engineered not to make systematic errors, I told you, right? Similar situation we have here. We have some true temperature that is now f of x. And I'm adding a zero mean Gaussian noise on top of f of x. What does it tell you about the distribution of y? It's going to be not Gaussian or Gaussian? Gaussian is going, so the y is exactly this one. Effectively, we are telling the story that my labels are Gaussian distributed with mean f of x and sigma squared, right? But I do not know f of x. So what is going to be the mean? Well, guess what is going to be the mean? What we replaced in the first discussion f of x with, what we call this hypothesis, g. So of x, I'm going to have g of x comma w. So effectively, my hypothesis is normal with g. Sorry, normal with mean g of x comma w comma sigma squared. So this is the question for you now. What SGD is now producing stays the same. Nothing is telling the stochastic gradient descent to do anything different. But the stochastic gradient descent output, which is the curve, is now, we are entitled now to call it the conditional mean. Because it's the mean of the conditional probability distribution that we call here as P model. This is my P model of y given x comma w. Yes. The G came from a very, very initial discussion we had about linear regression, when we started suggesting, hey, I have an underlying function f that no one told me anything about. I just need to start guessing it. And I started guessing it with various polynomial degrees to plot these guys, right? And I told you that these guys ultimately will be plotted and determined from stochastic gradient descent, because the stochastic gradient descent will minimize the mean square error, right? So now I'm connecting the two. I'm just effectively connecting the two in terms of equation, and I'm plotting the visual interpretation of this equation with this diagram. I'm plotting x versus y with the blue dots, the data points, as I had them before, right? And now I'm suggesting that for someone that gives me an x0, a house square footage, in other words, right? Given, in other words, the square footage of the house, what can you tell me about the y, right? Can you tell me a story about the y? According to the model we just wrote down, the P model, I will tell you a story about the y. The y is going to be Gaussian distributed. Where is the y-axis? It's obviously the vertical axis. This is the reason why the Gaussian distribution now is flipped, and it is the blue. The blue Gaussian distribution could be all the way to the ceiling, could be all the way to the floor. Someone will need to bring this Gaussian distribution to the right place. That someone is a stochastic gradient descent. Similar to what we were doing in the marginal setting. But in addition to the mean, which is right here, by the way, and this is my G of x comma w. In addition to the mean, the dot over here, this point, I now have the capability to ask the stochastic gradient descent, right, to also give me a sigma star.
And that comes all from the noise that you introduced.
From noise, because I'm introducing a Gaussian noise model. Now, this is a situation in x0. Vary this x0 from all the way to the left, all the way to the right. This is how you will get the red plot. There's going to be, however, only one sigma star square. And this is the limitation, maximum likelihood. The limitation of maximum likelihood approaches as compared to Bayesian computers, which are the most powerful computers you can build, is that there is no variability of the predictive kind of model across statistics, across the data set. In other words, the same sigma squared is going to be here, 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 and here. In a Bayesian computer, if you go to Netflix markets, there are some kind of dense markets like New York City with millions of data points, and some kind of remote rural areas, right, with some kind of few data points. So the Bayesian computer will say, you know what? If I predict a house price in this kind of dense space of prices, right, where I have plenty of y's, my error, my variance, will be much, much smaller than the variance in that rural area. I have very small number of data points. So the Bayesian computer always beats the hell out of the maximum likelihood computer. However, unfortunately, it does not scale. And this is the reason why at least in published settings, large, very large models, language models and things like that, they always are optimized according to MLE, maximum likelihood.
Can you use
Given, constrained on the computing resource.
Bayesian on the small language
You
model?
can use Bayesian, provided you can have enough compute to calculate, to account for the priors, additional, in other words, components that are present. In fact, if you go to Bishop's book, which is the original book he wrote, he has exactly the same example that we did in linear regression, but solved with a Bayesian approach. Okay. And then all of this stuff that I just told you is there, right, to enjoy if that's your thing. But are we in some kind of a good shape with respect to now that we have concluded? So now what I'm going to do is we concluded the regression kind of setting, and now we will start the classification task. Just to conclude the statistical learning for 2 tasks. And then we'll go home. Okay, so yes.
The 2 sigma there, that's because of the log?
Or it's because of the epsilon. Because of the epsilon. I included in the y the sigma squared as a variance. In other words, if I had a data set where the blue dots had a really large variability here.
But why 2 sigma, not sigma squared?
Okay, 2 sigma is because it has the Gaussian over there, and it accounts for 2 plus sigma minus sigma kind of.
What's the read?
Huh? What's that? Okay, the beta is think about the beta as 1 over sigma squared. Okay, it's just basically an expression called precision in statistics, where sometimes the stochastic gradient descent has a lot of trouble calculating things like when they are denominator, 1 over sigma squares, which are the denominator of the Gaussian. And they re-express it as a precision, right? Because then it's better behaving. So sometimes they optimize with precision, which is 1 over sigma squared. If you find a beta star, you effectively found a sigma star. Okay, so now let's start the classification discussion. So the headline is binary classification. And the problem we are going to see is there is a tower over here with some kind of a radar on top. Okay, the job of the radar is to emit some kind of special kind of signals where incoming planes are going to be, we're going to reflect the signals and return back a signal strength back to the radar tower. The same thing happens with your cars when you're driving with radar sensors in the bumper, because many cars now have the capability to maintain a constant distance, right, to the car in front of them. They emit signals, they come back with some response, which is kind of signal strength. They estimate, if you like, some velocity, and then they, with a control loop, they are optimizing the velocity of your car to not be higher than the velocity of the car in front of you. Okay? That same problem. Okay, so this plane, so the job of the receiver, so this is basically what's called a receiver. This system was deployed in World War II in Britain to warn against Nazi attacks from planes that were coming to bomb London. So this was many years old. And what was happening there was a guy, usually attacks were happening during the evening hours. There's a guy over there watching the signal coming back. And if the signal exceeded the threshold, was picking up the phone and calling London, and then sirens were sounding and people were running to the tube to save their lives. And so this is basically the situation. I will plot now a time series kind of plot of what is actually happening. So I'm going to call the received signal strength X. And this is going to be our only feature that we're going to assume that we know, because we can see it. We can observe it right at the receiver. And this is the time axis. And unfortunately, due to physics, multipath propagation and other stuff, the return signals are kind of noisy. So we have effectively two conditions. One is when we have an attack going on, right, it's going to be this red thing, red signal strength that is received over time. And when we have no attacks, we're going to have this signal strength X. As you can see, the signal strength is lower when we don't have attacks, but it's also noisy because there is birds flying, some reflections are happening from mountains, the sea level, whatever, they're coming back sometimes strong, and they overlap with signals when we have planes coming in. Okay, everyone understand now the setting? What is our job, however? The job is the following. There is going to be a quantity that engineers back then determined with solving analytical equations involving radio wave propagation, blah, blah, and so on. This quantity is going to be called W, and anything that exceeds W, that is going to be called the threshold, is going to sound the alarm. Anything below W, continue to nap. That's basically there is some kind of correlation between what's happening and here. All right, so continue to nap, sound the alarm. All right, so this effectively means that we have a binary prediction problem in front of us. We are going to determine the y hat to be 1 for anything above W and y hat to be 0 for anything below W. Now, y is obviously a binary random variable. We will call a positive event and represented with a 1, and a negative event represented with a 0. And a positive event for us, the attack is going on. Okay, sound the alarm. Okay, so that's basically it. So y hat is going to be, for the moment, binary also. Later on, the y hat, after the last discussion, y hat will be a number between 0 and 1. But right now, y hat is binary, discrete. Okay, so we are going to solve the problem of finding the optimal W. What is going to be the best threshold that we need to set such that two conditions are avoided? Before I go into this kind of conditions, we are going to solve the problem not analytically back in the day they were doing analytical calculations, but in a way that involves collecting data. So there is a guy over there observing what is going on. So it calculates for the first night, some batch of X1 and Y1. Second night, X2, Y2. If he gets killed, we replace with another guy, X3, Y3, etc., etc., etc. Finally, XM, YM is a last data point that we are going to collect, right? So we have now a table with a feature and a label next to it, binary label. Okay. So as you can see, the criticality of the W is kind of cannot be overemphasized. If we overestimate W, what's going to happen?
There will be an attack.
Yes, what's going to happen? Too many false positives. We overestimate W, in other words, put it too high, right? We are going to
detect false negatives.
We will not be detecting real attacks, people will die, for sure. If we underestimate W, we put it too low, what's going to happen?
Everything will be
Silence, first night, silence will sound, no attack will happen. Okay, fine, made a mistake. Second night, again, no attack happened. Well, maybe you should go down to the tube. Okay, let's do it. Third night, however, after that, people will just turn the other side and continue napping. And obviously, when attack happens, people will die too. Okay, they lose confidence in the reliability of the system. Okay, so we are calling with some kind of special names this type of conditions. And in a matrix, which is interestingly called confusion matrix, just to harmonize with whatever is going on here, right? The confusion matrix, and it's going to result into this matrix has two axes. The first axis is y and the second axis is y hat. Both of them are binary quantities right now. And therefore y could be either positive or negative, and therefore the y hat could be either positive or negative. Okay, so when we are predicting that an attack is going on, positive, and we are correct, we put a t in front of. This is called true positive condition. When we predict the y hat is negative, and we are correct, we are still put this t in true negatives there. But the other conditions that we just explained is when we predict a positive event is happening, and in fact we are wrong, we put an f, false positive, and the same thing happens here. Okay, now that we have the four quantities of interest, right, that are going to be involved in some metrics that we will see, we are going to sort of treat the problem probabilistically from the get-go. So I'm going to plot here two probability distributions. The first probability distribution is going to non-Gaussian. Okay, we're sick and tired of Gaussians anyway. So the first one is going to be called p of x comma y is equal to 0. And the other is going to be called p of x comma y is equal to 1. Now, and this is obviously x. So I plotted here the histogram of x when no attack is happening, and a histogram of x when an attack is going on. Now, any surprises why this is to the right of this? Why this is to the right of this? Just to understand whether we understand what a histogram is. Well, the histogram is a probabilistic interpretation of what's happening in the time series plot above. When there are strong reflections and attacks are happening, planes are coming in, obviously x is going to be larger than when the attacks are not happening. That's why the histogram is there. However, do you see the overlaps here in the color plot? Then this is the reason why there is an overlap between the right tail of this guy and the left tail of this guy. Okay, no surprises there too. So in general, we will never have a situation in this class where the two histograms are far away from each other. Yes, go ahead.
Do they sum to one point?
Yeah, this guy will sum to 1. And this guy will sum.
That's what I'm trying to say is like this probability of x, y equals 0 equals to 1 minus p of x, y equals 1. They receive for
Oh yes, so sorry. I mean the joint probability is just basically effectively you can call this class conditional probability. Class conditional. So it's conditional probability. Well, because I said that already given the y is equal to 0. So you can treat this as p of x given y is equal to 0, and this p of x given y is equal to So I want to write down the probability of making a mistake, an error, in other words, in this system, right? And given a specific W. What is a specific W? I want to plot a specific W. Obviously will be some, you see where W is located in the color plot, some value of X is going to be, some will be some kind of a wattage, let's say, right? Some, you know what a watt is, I guess, right? So it's like some kind of signal strength, right? So I'm going to basically suggest that W is right here right now. I'm setting this W to here, right, at this moment. And I am going to write down the expression of a mistake. Probability of a mistake. Well, the probability of a mistake is simply the probability of y hat different than y, which is equal to the probability when I'm making a mistake. In two conditions, you told me it's called false positive, false negative. Let's write down first. The probability of y hat is equal to 0 when the y is equal to 1, plus the probability of y hat is equal to 1 when in fact the y is equal to 0. Do you see the two components of making a mistake, right? Two components where making mistakes. Okay, so when I place the W over there in this kind of x-axis, I have split the x-axis into two regions. I'm going to call this region R0, and I'm going to call this region R1. And I call these names not accidental because anything to the left of W, I'm going to be calling for anything to the left of W or anything below W over here. My prediction is going to be there is no attack going on. Okay. So I am going to write down these expressions now as areas under the probability distributions that I just plotted. Okay, so we can understand visually that there is in fact a very special W that I'll call W star that is considered to be the optimal W star. I want to visually inspect what's happening and persuade everyone that there is indeed a W star. All right, so I'm going to draw this tail over here. And I'm going to draw this tail over here. And this area over there. Okay. So I could continue. Now, look at the expression and tell me if you agree with what I wrote. When I'm making the prediction of y is equal to 0, y hat is equal to 0, when the signal strength is in the R0 region. And then I'm taking it on the other side when the signal strength is in the R1 region. Do you agree? Anyone? Yes? Yes, yes, go ahead.
So just first term corresponds to the green lines.
No, we'll see what it corresponds. We'll see now in a moment. Okay. But you agree with this equivalent expressions. I wrote an equality here, so I hope you agree. That's when we predict that y hat is equal to 0 and y hat is equal to 1 respectively. So if I want to estimate probabilities, I'm estimating probabilities of a continuous probability distribution, right? Of a quantity like x is continuous. It's going to be an integral, if you remember from school, an integral under the PDF curve between this point and that point. Take the integral, whatever is the probability distribution, that is the probability of something happening in some region. We cannot, of course, say a probability of a x1 is equal to 0.357 because that's 0. We discussed that already, but we can definitely have a non-zero probability in a region. So what is this integral for this specific term? What curve, to go back to your question, we are looking at to estimate the integral of? Definitely, the integral is an region integral, R0. It's an integral over R0, right? Of which probability distribution? When do you see that? This is a critical point. So this corresponds to, I'm looking now at which of the two probability distributions, the right one, and I'm looking at the left tail of the right one that falls in the R0 region. Plus R1 P of x comma y is equal to 0 dx. Now I'm looking at the right tail of the left probability distribution. So is the first integral a false positive or a false negative? What are you going to
False
do?
negative.
Huh?
False negative.
It is a false negative. If you trace it back all the way to the first expression, you can see that this is definitely a false negative event. In fact, because it's probability, I will call it a false negative rate. This guy is a false positive rate using exactly the same reasoning. And I want you now to start moving W. In fact, I want you to start moving W to the left slightly. What's going to happen? The area of the corresponding tails will change. The green and the summation of the green and the magenta area will shrink, and the orange area will expand, will grow. This thing will continue until this point that I will call W star. In this point, as this area moves, whatever we are losing from the green, we are gaining it from the orange. However, one region over here shrinks and shrinks and shrinks all the way to 0. What was this left tail of the positive one was called? False negative. So I am shrinking the false negatives, and what happens? I am growing increasing the false positives. So I'm trading off false negatives for false positives, false positives for false negatives. And therefore, we can claim that is false positive rate and false negative rates are trade-offs. You're always going to make mistakes. Your best strategy is to minimize the total number of mistakes. The total number of mistakes is minimized at the W star because the W star is the point where the summation of the green, the orange, and the magenta regions are the minimum possible because the magenta disappeared. So visually, we are now persuaded that there is an optimal point. W star. And the question becomes, who is going to provide the W star for us? Okay, that's another question. Okay? This W star is going to be the optimal threshold. As we'll see, despite the fact that I called it W, this is not the same W as we had seen up to this moment in time. In fact, I should have called it theta, but because I made a mistake 3 years ago. I continue the mistake in terms of notation. So this theta is not the W, because the W we used to all know are the parameters involving the hypothesis, right? We have not discussed anything about hypothesis up to this moment in time, because this diagram is applicable for any binary classifier. Could be a very gigantic neural network, or could be a very simple classifier we'll see in a moment. But this situation can happen for any hypothesis complexity. Yes, probably.
If the W star is the threshold, right?
Threshold, it's called threshold, right? I mentioned that. So this guy, in fact, we'll see that a threshold is a far more quantity which is amendable to non-optimization techniques, right? In a sense that we can set it depending on the business and the use case. So, for example, if you have a patient that out of computer vision will determine whether they have cancer or not, obviously, you are willing to trade larger false positives for smaller false negatives. Because what's going to happen with, sorry, you're willing to minimize the false negatives. Yeah, that's exactly what I said. Minimize the false negatives, because if you say, hey, you don't have cancer, go home, obviously they will die. But if you say, oh, you have cancer, they don't, you will hit them with chemotherapy, probably will survive, right? So in that kind of settings, as compared to others, you have different trade-offs. So you have to always consider which one is the right W for me, or the threshold for me. You can find the W star also with optimization kind of algorithms and optimal kind of thresholds. But typically what we do is we don't use them. Okay, here's however some kind of a discussion to generalize what we just discussed, the probability of mistake, with some metrics that we will call classification metrics. And classification metrics will involve two quantities for now. The first quantity is called the ratio of, so it's called true positive rate, recall, probability of detection from the radar tails, sensitivity. All of these terms are equivalent. They have been invented into multiple domains, and to denote exactly the same thing. This ratio of true positives divided by true positives plus false negatives. The other metric is called precision, and it's a ratio between true positives and true positives plus false positives. Recall is the term that we use in this domain. I told you, and I showed you a few moments ago, that there's a trade-off between false positives and false negatives. Therefore, given these equations and the fact that everything is otherwise the same, I can claim that there is a trade-off between recall and precision. Do you see that? For those who are paying some attention at least. Okay, so, all right, so there's a trade-off between recall and precision, which is going to stay for us, obviously. And this trade-off is going to be captured with certain curves. One of these curves we'll actually do today is going to call the receiver operating characteristics from the later days. And the other one we'll see when we do object detection, which is going to be the recall versus precision kind of curve. Because over there we'll see the metrics. Okay, as well, because there are involved also in object detectors. Having said that, I think it's going to be some kind of intuitive way to remember always this recall and precision, and always remember what is the best thing to do, right? So imagine that you are have a table over here full of gold coins. Imagine that. But at the same time, there is a banana as well on the table. Okay, and so what you're trying to do as an sort of optimal kind of detector or classifier. First, you try to gather all gold coins, leave the banana behind. The banana is your false positive. At the same time, so something to remember as the so you, all of the possible gold coins you can get. This makes a little bit more sense in the object detection, because in object detection we don't have false negatives, right? But you try to get at least all of the true positives that are there, leave the false positives behind. Let's finish with the receiver operating characteristics, or ROC curve. The receiver operating characteristic captures the recall versus the false positive rate. False positive rate. And it will look like this. For recall, as you can see here from the ratio, when the false negatives is 0, right? The maximum possible recall you can have is what? 1. The false positive rate obviously is a probability, so the maximum false positive rate you can have is also 1. Okay, and therefore all the receiver operating characteristics are going to be like this. So they are going to, in fact, going to look like this. I'm going to plot 3 of them. Okay, supposed to be. So this guy is A, this guy is B, and this guy is C. How do we plot each curve? Well, you can trace the answer back to what we just did. The only thing that we have in our disposal is the threshold. For each curve, we are varying the threshold, and we start gathering false positives and false negatives, right? And with that, we are plotting this curve with this information. A, B, and C, however, they are not plotted with varying thresholds. The A and B and C correspond to different classifiers. We have not even seen a single classifier in front of us, but we're entitled to plot its ROC for now. Which classifier would you choose, A, B, or C, to be your classifier? Yes. Which one? Come on, you can do it. Yes?
First, A.
A. Okay, so it's easy to see why it is A. In fact, I can write A better than B, better than C. For the same probability of false positive, the classifier A offers the highest recall. Or equivalently, for the same recall, the classifier A offers the minimum probability of false positive. Classifier. So in fact, there is a point, this point that I just drew, that is the best operating point, as we call it, because at that point you have recall of 1 and FPR of 0. Remember the points and the banana. Okay, all right. So that's basically called an ROC curve. Receiver because of the radar kind of legacy. Operating characteristics because I, at the end of the day, I have to deploy a classifier with one threshold, right? I have to choose an operating point that I'm comfortable with. That kind of operating point, let's say, is the red one, is very close to the optimal one. One way of choosing it is like this, but as I said, depending on the use case, you are entitled to choose other type of other thresholds. And we are going to conclude tonight with doing two things. We saw the metrics, we understood what's happening in the binary kind of classifier. In order for us to come up with a block diagram of a classifier, let's first discuss how we are going to optimize its parameters, whatever the block diagram is. And for that, since we presented in the classification discussion probabilities and histograms and things of that nature, we are adopting straight away cross entropy as our maximum likelihood objective function or loss function for binary classification. And we're going to write its what is called the binary cross entropy loss for classification. What is the cross entropy formula? That was basically it, which is equivalent of writing cross entropy of y hat comma y, because behind the y hat there is a w, which is what? Minus expectation x comma y distributed according to b data hat log p model of what? Y given x comma w. I cannot close the parentheses, but you can imagine. Okay, that was the general formula we saw in the conditional model we had in regression. Still applies in classification, a very general thing. What we did in the regression is we plugged in the P model. Instead of P model, we plugged the Gaussian model, right? That has to do with the variability of the Y's, if you remember a few moments ago. Can I do Gaussian here? I can do whatever I want, but does it make any sense for me to apply a Gaussian P model for the Y? No, it doesn't. The reason why it doesn't is what? Because the Y is a discrete random variable. And the Gaussian probability distribution, last time I checked, which I advise you also to check, is for continuous random variables. Okay, so I need to go to Wikipedia and say, okay, search in the old way, discrete probability distributions. In fact, for binary classification, there was a very appropriate probability distribution. And also we saw when we looked at coin tossing. Remember the heads and tails that we looked at the entropy? Well, the head is the y is equal to 1, and the tail is, let's say, the y is equal to 0. So that probability distribution is called Bernoulli. Thank you. So our P model here of y given x comma w is equal to Bernoulli is equal to y hat to the power of y. It's now I'm writing exactly the equivalent of 1 over 2 pi sigma squared and stuff like that. I was writing when the P model was Gaussian. I'm not really doing anything smart here. I'm just going to Wikipedia, copy the Bernoulli equation from there and write it down with my own notation. In fact, if y is equal to 1, when there is a positive event, what is this P model is giving us?
Y hat.
Correct? This is kind of important because a binary classifier will spit out now not absolute 0 or 1. Will spit now a number between 0 and 1 that we have to interpret according to what the P model is telling us. We are not interpreting according to some form of sort of intuition. This is an equation here. What is the interpretation? Can I ask, how would you interpret the y hat given this equation I just wrote? It's called the probability of the positive event. The y hat, in fact, is called the posterior probability of the positive event, because, and this is this formal kind of name, because this y hat can only be obtained after we observe x. After we observe, that's called posterior probability. Posterior probability of the positive event. In general, all of these guys have underbars because they're high dimensional coordinates. So this guy is called posterior probability of y is equal to 1. This guy will have cancer with 0.83. I'm immediately conveying my confidence to you, which means that he won't have cancer with 1 minus 0.83, which is effectively what y hat is giving you. This is going to be obviously the P model of y is equal to 0 given x comma w. If you plug in the equation. Okay, since now we have a P model, which is Bernoulli, all I need to do to write down the binary cross entropy for when it's going to be called binary cross entropy when we have Bernoulli, and we have a multi-class cross entropy when it's multi-Nulli, when we have multiple classes, right? So now we have just 2 classes, so let's write it down. So I'm going to write down only the log of the P model, and then I'll replace the expectation with the sample mean. So I'm going to write down as log of y hat to the power of y, 1 minus y hat to the power of 1 minus y is, you tell me, what? Log of y hat to the power of y plus log of 1 minus y hat to the power of 1 minus y is equal to y log y hat. I'm not doing anything other than elementary calculations here. Log of 1 minus y hat. Do you see that? I mean, I hope there are no disagreements. That is basically the inner term, so to speak. Now I'm entitled to write that the binary cross entropy of y hat comma y is equal to minus 1 over m summation I is equal to 1 to m of this thing here, yi log of y I hat plus 1 minus yi log of 1 minus y I hat. Is this a real number or not? Is this a vector or a real number? No one understands if it is a vector or a real number.
Real number.
It is a real number. And in fact, this is real number. I want to plot this guy just to see how it behaves, because I cannot plot the real number versus something across all examples. But I would just want to plot the per example loss. Is this loss, by the way, the binary cross entropy, difficult to calculate or easy to calculate? Easy, because you are given the yi's, and your estimator, your classifier, is always spitting out a y hat, right? So very trivial to calculate. So I just want to plot the what is called here per example loss, which is this term over here that I indicated, versus y hat. What is y hat again? It's a prediction, but what corresponds to? The magenta interpretation. It's a probability of the positive class. Therefore, what's the maximum value of y hat now? 1. And I am going to plot it for a given, because per example, this specific example I'm considering has a ground truth of 1. You can plot it for ground truth of 0. It's the same thing. Nothing changes. The shape, of course, will change, but nothing changes other than that. So I have a positive example, and I have two cases here. Y hat for this example is 0.95. Just so happens that the classifier says 0.85 for this example, and which is actually over here, right? And do you expect the loss to be large or small?
Small.
Small, because the ground truth is 1. You say, I'm 95% confident that it's a positive decision. When y hat is 0.05, what do you expect the loss to be?
High loss.
Very high, because I'm saying I'm 95% certain that there is a negative example in front of me, right? So I'm completely wrong, right? Because the ground truth disagrees with me. In fact, if you plot a curve, you'll get a curve such as this, right? So when y hat is 0.05, very high loss. This, I will call it asymmetry in the losses that is being sort of exhibited by this kind of a binary cross entropy and averaged out across many examples, obviously, is the reason why we can actually write that the binary cross entropy penalizes heavily confident wrong decisions. I wish all decisions were penalized like this. But anyway, the confident wrong, because I am confidently predicting that there is a negative example here. It's 0.95% with 95% certainty. Right? I'm getting hammered because of that, of the shape of this. All right. So now that we have the sort of loss function, we are entitled to draw the block diagram to see how the stochastic gradient descent will calculate the weights, the parameters of whatever classifier we throw at it. All right, so how the block diagram will actually look like? Well, the block diagram will look like this. There's going to be some predictor that is going to spit out a y hat or an x. Then obviously there's going to be a binary cross entropy that requires obviously the ground truth to be estimated, to be calculated. Some kind of a loss will be produced. And the stochastic gradient descent, knowing the functional form of the cross entropy, which I'll call here L as a function, L graphic L, with hyperparameter MB, as we discussed many times now, we'll use it to do the parameter update. And change the parameters doubly over time. Similar what we have done earlier. And to close the whole discussion, let us just see a primitive classifier, just like we saw a primitive regressor that we call a linear kind of model. Now this classifier will be called a generalized linear model because it will contain some nonlinearity that we need to understand where it came from. We need to understand where the nonlinearity came from. That classifier is called a logistic regression. Now, block diagram wise, the logistic regression will be identical to what we call a neuron. This will open up the possibility to almost with some certainty, be able to enhance this classifier with some kind of combination of neurons. That will give some kind of discussion about neural networks next time. So logistic regression can be, I will call it, presented in two ways. One way is through a Bayesian rule. The Bayesian rule, and that way is described in one of my YouTube videos. You can entitled to watch it. But here I'm going to present it in a way which is kind of a little bit visual and close the discussion. So the block diagram wise, the logistic regression will actually be an x goes through a featurizer, a phi of x is coming out, just like in linear regression. Just like linear regression, there is a linear stage, a linear combination of features, in other words, that is obviously implemented here with the dot product. And then the scalar that comes out of that, every dot product, obviously, is passed through a nonlinearity, which is called the sigmoidal unit, or the sigmoidal activation function, to produce a y hat, which, as we know, is our P model of y is equal to n to 1 given x comma w. That is the block diagram of the logistic regression. Now, why is called a regression and you're telling us it is a classifier? Well, the reason is that you are trying to solve a problem that you have in a typical way. We're solving problems in regression. In fact, I remind you that the only thing that these regressors are receiving are just the blue dots. And instead of blue dots, I'm going to use blue dots here. So over here, I have some kind of blue dots. And tell me if you agree that in the binary classification, these are the blue dots that someone can give me, or I can obtain from recording actual data. And the reason is that over here, while previously the y was a floating point number, over here, y can only receive two values, either 0 or 1. And if you go back to that radar example, when I have small x's, small returns of signal, then I have no attack going on, and the y will be 0 most of the time. And when I have high x's, the y will be 1 most of the time. And in between, there will be some noise in the overlapping region, if you remember, right? However, if I try to solve this problem as a regression problem, I will be entitled to draw a hypothesis such as this. And if this hypothesis is drawn, I immediately recognize that this hypothesis can result in some values of x with y hat being less than 0 or y hat being larger than 1. You can see that right here in this region. I can go to this x for this hypothesis, my y hat will be negative. And over there, for some large x, my hypothesis will result in the y hat being larger than 1. That doesn't make any sense whatsoever. So what I will do is I will use a compressor, a compressive function called a sigmoidal function, to effectively compress that hypothesis in such a way that everything is between 0 and 1. So I'm solving the problem as a regression, but at the same time, I'm taking care of the output to make some sense. That is the hand-wavy way of presenting logistic regression in a visual, completely visual way. Now, if I take this and hit it with binary cross entropy and apply stochastic gradient descent, I will, for some classification kind of problem, I'll have no problem whatsoever to get a very nice result. In fact, I will use this example over here, which is a binary classification data set, where I have how many features? How many features I have here? Two features. I have x1 and x2. Every point is a point in a two-dimensional space, therefore has two features. And how many classes I have here? Two classes. I have two features, two classes. All right, so the features are x1 and x2, which are the axes of my space over here, this guy and this guy. Every point that someone is giving me is an x under bar with x1 and x2 as the coordinates of this point. And I have a label. The orange is a 0 and the blue is a 1, let's say. I have a label associated with every example. And I have a binary cross entropy optimizer. I have a sigmoidal nonlinearity at the output. I have a learning rate. And I am going to press the play button, and stochastic gradient descent will very easily converge into a decision boundary, offering me a decision boundary, and therefore an optimal parameter vector W. Do you see that? That's it, the end of the story. Now, if I go from here,
Professor,
yes.
I think right now it's using the tan H activation and not sigmoid.
Oh, the sigmoid, okay. It doesn't matter. It will do exactly the same thing. Now, things will become a little bit different when I have a slightly different problem, though. Still binary classification. Still number of features 2, right? the thing is trying to, obviously, ideally, is to come up with a decision boundary, which is now a circle that is going to be positioned, right, between the two classes to be able to classify them. But it cannot. Which, of course, is something we saw already in linear regression when I drew a hypothesis which was parallel to the x-axis. This was called underfitting. We had to increase the number of parameters to the right size, right, and apply regularization as well, in order to come up with a right hypothesis. So next time, we'll do exactly the same thing. We will start increasing the number of parameters by connecting these logistic regressors, or neurons as I will call them, together in some kind of architecture. And we'll call this architecture the dense architecture. And then we'll see what they can do. Can they solve this problem, yes or no? And how we actually can have now a discussion about multi-class classification, because obviously we need to understand that not everything is a binary classifier. We may have 10, 20, all the way to 1,000 classes, for example, in some supervised learning settings. So I'm going to close now the lecture 5 minutes early.
You want to take attendance?
Yes, someone has my attendance sheet. Anyone who did not sign this thing has to sign right now. I'm leaving in 5 minutes. Let's do it. Go. If you have any questions, please come and see me. I'll stay here until 7:20 because I have to retrieve my car, okay?
Like a few minutes to talk later.
Yes.
Yeah, I have a question like just regarding like how like the class is graded and stuff. I'm a specific issue. I also wanted your like a research project.
So do you want to open a ticket and find a time to talk to Zoom?
Sure.
Yes, open a ticket and then we'll find a time to talk to Zoom.
Yeah, on Discord.
Discord, yes.
Okay.
What's your name?
Suhas.
Suhas, okay.
Yeah, I like registered late, so I just joined the Discord.
Okay, no problem. Yes.
I just joined this course.
You just joined the course
Yeah.
today?
Yeah. So this is like it's a bit of a
So
but
there are two things that I need to do. First,
Yeah.
I want to make sure that the permissions in the Zoom
Yeah.
are open, so you can watch the previous video.
yeah, I was
It's been recorded.
okay.
But on meantime, my videos are in YouTube in the media section of the website.
Got you.
Start and watching them. And then you need to open a ticket in Discord. In one of the videos, I will explain how to use Discord.
Yeah, I'm in the Discord right now.
So
So
open a ticket and ask for an extension for assignment 1.
okay.
And I will need to approve it. And I'll give you 1 week is enough.
Yeah. Yeah. Got you. And the Zoom they'll be up.
The Zoom is going to be in bright space always. It's just that someone told me they are not able to watch it because they don't have permissions. But something happened. It should be there. It should be there. It is there. It's just me sitting and changing the permission.
Okay.
Professor, what is the sigmoid squashing function you were talking about?
The sigmoid squashing function is 1 over 1 plus e to the power of minus x.
And
It's a format, it's a deterministic function.
did we have to use that today or no?
We used it already, even on the demo in the test ground. The sigmoid was there, but selected it, and the banner was also there. Just was not there.
Okay. Thank you.